Hello class, welcome to the second to last week's module. This week we're going over regression discontinuity design. To give you a quick overview, regression discontinuity, it ultimately helps us to address for selection bias. Also, you could refer to it as endogeneity, omitted variable bias. All of these are ways or forms of introducing bias. But really, the way that this is important, or the situation in which this applies, is when you have a program cutoff, so a treatment program where you qualify or where you don't, where that differentiation is a clear defined cutoff or a score, also known as an assignment variable too. So think of like a test score. Got a little example mocked up here for you. Let's say we want to look at a scholarship program where in order to qualify for the scholarship, you have to have at least a 70% score. Anything below that does not qualify. Anything above does. So ignore this 68, 72 for right now. So let's just say we have our 70% cutoff. Anything below, not in treatment. Anything above, in treatment. So what regression discontinuity utilizes is when we have a situation like this, we can say, of course, the lower end and the upper end are different. There's a lot of inherent differences or selection bias that we might incorporate if we look at each of these. However, if we narrow it down to just look at this group close to the threshold, so let's say 68% to 72% scores, that tells us that that group is not necessarily very different. They probably studied similarly in preparation for the test. So what we're really doing here is we're going to turn this small group into our sample set. So we're going to have a control and treatment. Control being those who did not receive the treatment, who are below the threshold, and those being in treatment, those who were above, because again, those are the ones who get the scholarship. And we're going to talk about mean centering later, which is a big part of this. Something you've probably noticed is that as we go through each of these models, the LM function is virtually the same for all of it. We do the LM function except for there's some more specific packages to different types of models we've gone through, but you can use an LM all the same. But the difference is really how we prepare the data in order to run the regression. So with this one, we're going to be doing something similarly where we do the mean centering, but I'm going to get ahead of myself. So let's touch base on it just a little bit again. Selection is one of the most challenging problems in evaluation, and that occurs when participants decide whether or not to participate in the program. They select into the program that inherently makes them different. So this means that program participants are different from non-participants, thereby making our observations or results, if we were to use these groups, biased. So again, those who opt into a program are different than those who don't. And this is synonymous. So selection and omitted variable bias are synonymous. So as an example, again, let's say we want to look at people who go to the gym and whether going to the gym, pardon me, lowers heart disease. So if we were to look at data of people between 30 and 40 that actively visit the gym each week, and then those who don't, we would have an apples to oranges comparison. Reason being is those who go to the gym are likely inherently different in the sense of they probably have very different diets, other lifestyle factors, perhaps health concerns would more weigh into those who don't go to the gym, or that there's a virtually never-ending list of possible differences. So by using this example, we would introduce a lot of bias because these are apples to oranges. They are not the same. They're too different. So the regression discontinuity, otherwise referred to as RD, it was created to deal with this very specific type of selection. So cases where people have to qualify for the program, and the criteria for qualification is a measure that is highly correlated with performance. So again, something like scores or scoring on a test in order to receive a scholarship, something along those lines. And I don't think I mentioned it yet. We're going to primarily discuss just your traditional threshold where it's a very clear line. So that's generally your regression discontinuity design or model is where you have a very clear cutoff, like the 70% we talked about. There's also something we cover at the very end called fuzzy regression discontinuity, and that's where you don't have a super precise cutoff, and there's a little bit of a range for the cutoff. So let's say the range became 65 to 75%. So that's something that we'll look at too, just very briefly. For I think almost all of our purposes, we're just using examples with a very clear cutoff. So as another example here, standardized exam. So it's used to determine honors classes, whether students place in honors classes or not. So let's say we want to measure college GPA and see whether or not honors classes were to improve college GPA. And we have a clear mark where we have the threshold. If you score whatever this is, let's just call it 80%. Terrible 8, but we'll run with it. Let's say you score 80%, pardon me. 80% is the cutoff. Anybody who scores above 80% gets into honors classes. Anybody who scores below 80% does not. And we want to look at college GPA down the road. Really what we're looking at here is not the whole group, because that would introduce a lot of bias, but instead this group right here, because we can argue that this group is not very dissimilar. We can argue that they're similar. They probably studied very similarly for the test, have similar underlying competencies. So really it's about honing in on this subset here in order to try and determine treatment effect. As another example, let's say if you scored below, you went to summer school. So if we wanted to see the impact of mandatory summer school for those who scored below a certain threshold on college GPA later, once again, the cutoff is very clear. We can call it 80% again. And this is the group we're looking at. Now, if you had all the data, you could do a diff and diff. So if you have the, pardon me, if you have the performance data for both groups before and after the program occurs, then you can use difference and difference framework to compare gains across the two groups and parse out program impact. But if we're using post-program administrative data, or if it's impossible to measure performance prior to program completion, for instance, there's no pre-program college GPA, for example, in the examples above, then regression discontinuity is appropriate. So there's a few other examples here where we have these uh, clear cutoffs, tutoring programs where if you score 50 or above, 50 or below, you get reading tutoring for reading. That would be the treatment group, while students who score above 50, they're not included. In this situation, that would be our control group. Even a program like Medicare, those who enroll by a certain age, the older ones, pardon me, they would be considered the treatment group. So I think it's 65 for Medicare. So those who are 65, probably not too different from those who are 64, and so they would be very similar. But the 64 would be the control group because they're not able to receive Medicare yet, and those over 65 would be our treatment group because they are receiving Medicare. Uh, like rent subsidies, we have certain income thresholds, and then if we were to look at college admissions, so facilitates admission, excuse me, to college for the top 10% students from low-ranked high schools. Students in the top 10% will be part of the program's treatment group, while students below the 10% will not. That'd be our control group. So again, the problem becomes endogeneity, which is again synonymous with omitted variable bias. It's one of our uh, variables is associated with the error terms of the outcome, and so that introduces bias. And this once again helps us to control for the selection bias. So this is another example. Let's say that we're working with scholarships, and let's say it's offered to low-income students who attend college. You can see a model below. We'll look at that. The x-axis is going to be the income. Uh, Now, something really important too is that this is referred to generally as a rating variable. So the rating variable most often, or I think almost always, being on the x-axis, while the y-axis is looking at the outcome variable, so our dependent variable. So if we look at this, we can see that there is a positive relationship between family's income and college enrollment. And let's say that we want to establish a scholarship for students below a given level of income. This is going to be the cutoff or the threshold as we previously saw. So we have two groups. One group receives the scholarship, that's our treatment group, scholarship being the treatment, and the other does not. So we have an income cutoff right here. We have our control group here not receiving it, and we have our treatment group here below. So below a certain threshold, you receive below a certain income threshold or cutoff, you receive the scholarship. So if we were to just compare these groups, though, this is problematic because once again, students who did not receive the scholarship are more likely to go to college even without the scholarship because of their income. And that's again because we have a positive relationship. If your family has more income, you're more likely to go to college. So if we were to just compare it this way, it might actually appear that our scholarship program had no effect, but it doesn't imply that necessarily. So in the model, it might not detect um, a significant perhaps outcome because of that, because we're working with a group who otherwise without treatment would have been less likely to attend college. So once again, it might be that in the absence of treatment, without the scholarship, low-income students would have been less likely to enroll in college. So RD, it's going to be used to solve a problem like this, and it assesses whether or not, it assesses, pardon me, whether or not we observe a treatment effect. So it does this by accounting for the relationship between the outcome and the rating variable, and then calculating the difference between the two groups. And we can see here, sort of like our interrupted time series, we have the break. This is a way that we can measure or we will visually see the difference in treatment. The treatment effect. But once again, referring to endogeneity, that's going to be the correlation between the explanatory variable or the treatment and the error term. And so, if the outcome of the assignment of treatment, which might bias the estimation of the effect of the treatment. So low-income students might continue to enroll in college at a lower rate, even with a scholarship, leading to a downward bias of the estimates. So it may appear or look in our model, our results, that there's actually no effect, when really there is. But when we're working with groups in such a way, it might appear otherwise. So similarly, low-income populations receiving a subsidy to pay rent might continue to have more housing issues than higher-income individuals. So individuals who receive Medicare, they might have greater health problems because of age, and without controlling for the relationship between age and health outcomes, we might have a downward estimate of the effect of the program. So RD, it allows us to estimate the local treatment effect comparing individuals close by the cutoff point. So ultimately, we're looking at the group close to the cutoff point. All right, now moving into the statistical model part of me. And sorry, actually, to pull back just a tiny bit, y'all. There's a lot in here. The bottom line is we're really just focusing on this area. So don't get too caught up in anything. Just know that when we're working with it, we want to start to focus on. I think there's other ways to refer to it, but people at the margins. There's different terms, but we're just looking at the group close to the threshold or the cutoff. All right, so looking at the model. So you'll see once again, it's very similar to every other model we've worked with. Y is our outcome. We have a dummy variable indicating treatment. The rating variable, though, this is the one that's going to be different. This will tie you back to, pardon me, look familiar to you from one of our previous ones. Fixed effects, where we had to do some of the mean centering. So in this case, we want to center our mean, and we do this by subtracting the cutoff score, so whatever that point is, from each individual score. And then that's going to become our new intercept, so we'll have a single cutoff. So cutoff minus cutoff equals 0. That gives us a 0 for that. Ultimately, it's going to look like this. So let's say that our score value is 20, or our cutoff score value, excuse me, is 20. And the scores, we're going to take each individual score, 10 minus 20, 30 minus 20. And then, like we did previously, I think it was fixed effects. Ultimately, we're centering that. So we're just playing with the value a little bit, and that allows us to get or do the mean centering. And you'll notice here the rating variable C, so that helps us to differentiate the difference between the actual rating variable itself and the centered value. Now, when we consider the coefficient, so beta 1 is going to represent the difference between the treatment and the control group, and that's going to assess whether the intervention had an effect. And then beta 2 is going to represent the relationship between the outcome variable and the rating variable, and it allows us to control for the endogeneity in this relationship. So our counterfactual in this situation, so let's see, we're working with the scholarship still, so the income, so family income, and college enrollment. So students who fall below a certain income threshold will receive a scholarship, ultimately incentivizing or encourage them to um, enroll in college. So in this case here, our counterfactual is going to be this the same intercept and the same slope that would have existed. Now, once again, we do this by assuming that the intervention had not even occurred. So we just set our treatment to 0. Once again, the dummy variable saying it had not occurred, and we can calculate. That's how we get our counterfactual. All right, so now we're going to go into another example here. So we want to look at the relationship between class attendance and student performance. And I'll let you read through and look at this a little bit more. But ultimately, we want to imagine that there's three classes of college students, assigned students who have an attendance rate lower than the median to a treatment group. And that treatment would be subject to a mandatory attendance policy. So that's our treatment group in this instance. And then the students who have greater rate of attendance above the median, that's going to be our control group. They will not have the mandatory attendance policy. So our hypothesis, a mandatory attendance policy will increase the final performance of students enrolled in treatment. So we're working with their performance. That's the final exam grade, the treatment, whether or not they had the mandatory attendance policy, their attendance itself, and that's going to go from 0% to 100%. And then we have our centered value. So attendance variable centered around the cutoff. The cutoff was fixed at the median. So the median or the cutoff here is just the median that was calculated. So we have some of the data here. Now, the problem again with just comparing the treatment and control groups, if we were to say just measure them by the averages for each group, the control and the treatment, that would introduce some bias because our groups are going to be very different. Where our lower attendance, the treatment group we're looking at, they're more likely to have lower grades than students with higher attendance. So if we were to just compare the means of the two groups, we might observe no actual difference between them because once again, we don't have it. Oh, similar to this, the effect might not look very much different because the control group in both these situations are the higher performing, and so the increase may not be noticeable because it's not significantly better than the control. Hopefully that makes a little bit of sense. We'll go through a few examples as we go through. That should clear it all up. Okay, so we find the average performance of our treatment group, or the average performance being the final exam score, if I'm not mistaken. Yeah, final exam grade. And then we do the same for our control group, those with better attendance. So we see a 76 there, 57 here. So if we were to just look at the means, we would conclude that the treatment had no effect, but that's not necessarily a fair way to look at it. So like I mentioned before, LM is going to be the same as most of our other models. We're going to do the same thing, our outcome variable, treatment variable, and then in this case, we're using our attendance, but the centered value. And we can see our coefficients here. So we can see our treatment had a positive and statistically significant effect. Attendance itself, sorry, before I move on, so let's recap. So beta 0, that's going to represent the performance of a student exactly at the cutoff point. Beta 1 will represent that, it's positive and significantly different from 0. Pardon me, I'm actually going to start that over. Let's just do it this way. So the treatment variable, that's going to be, again, the actual effect of our treatment. That's going to be represented by, we don't have a visual. That's going to be represented by the jump. Like in our interrupted time series, we saw the immediate change in intercept. Let's see, where was it? So that's going to be represented by right here. This. That's going to be our treatment. So I'm going to put it here and up there. So change in intercepts. So according to ours, our treatment showed, this is in terms of final exam grade and the treatment itself. So I'm not sure if the final exam grade is from 0 to 100% or if this is points. Without knowing explicitly, it's hard to translate 100%, but ultimately it's, we'll just call it points. Yeah, let's call it points. So this is saying that by being in the group where the mandatory attendance was required or implemented, final exam grades for that group went up 7.03 points, saying that it's a statistically significant and positive increase. So once again, that is our break. That's the change in intercept. Now the attendance component, this is the representing the, and I want to set the stage for this. So this is using the attendance centered variable. We'll shortly look at how we can not use that, but that changes our interpretation. This, however, when we have it with a centered variable, is representing the slope. So this is saying, since our attendance was in a percentage from 0% to 100% in terms of total attendance, with our attendance being represented still, even though we centered it, it's going to be representative still of that percentage. So our attendance coefficient, this is going to say that for every 1 unit increase in attendance, which our attendance is a 0 to 100% of total attendance, So for every 1% increase in attendance, we can expect a 1.16 point increase in our final exam grade. Now, and sorry, I might have misspoken. So the thing to keep in mind that I'm going to get into here shortly is the constant. Depending on whether or not we use the centered rating variable, in this case, attendance centered, if we were to just use attendance, what that's going to do is change the interpretation of our constant, which I'll go over shortly. So again, that's how we're looking at it. So the treatment will represent the change in intercept or program effect. This is going to represent the slope for every 1% increase in attendance. We can expect a 1.16 point increase in final exam score. And sorry, here our constant, let me come up visually, I'll show it to you again. I don't know why the notes didn't include a visual down there, but it didn't. So here we have our treatment effect. The intercept, the constant, is going to be representing our control group's intercept right here. Okay, so that's what our constant is representing. So that's saying for our control group, when our centered attendance score, remember we centered it, so anybody at the center here will be at 0. So it's saying this is the intercept for the control group when attendance is 0, meaning at the cutoff because we centered our values. Okay, so don't get too caught up on that or confused by that because shortly we will be looking at how we can leave attendance as is, and again that changes our um, interpretation. So let's just recap that here. So I'm going to put in with attendance. Oops. Attendance centered. This represents our control groups expected at the cutoff. We would say this is our control groups constant. So again, if we're looking just at this, oops, the model's looking just at this narrow section here in order to determine our values. So looking just at that, the constant tells us the control group, which would basically be the same as the treatment group had they not had the treatment. Um, this centered area right here, or pardon me, this threshold area right here, our constant is saying the control group at the cutoff. That's our average score we would expect. The treatment coefficient, though, is again expressing that change. So our example in this output here in the situation, we would say that our treatment group, because of the treatment, that threshold area, those students would actually score 73.44. So it's additive, our constant plus our treatment. So treatment represents the difference between the score from the intercept, the constant here, and the treatment. Okay, hopefully that makes sense. Don't get too, it's pretty straightforward, but sometimes it can get confusing. Either way, let's move on. This is what I was getting at. This box here explains the uh, common practice of centering the score or the rating variable. So in ours, it's centered, that first model we ran. And so all of the intercept part of me is located at the cutoff point, and that represents the average final score of a student with median attendance. Again, for the control group. So it represents that. So it's essentially saying the attendance is 0, but that's because the attendance is based on, in our situation here, the attendance is based on the cutoff score, and so the threshold right in the middle is going to be at 0. So when we do our mean differences there. So all that to say, it is possible to run the model without centering the score, but like I mentioned, the interpretation of our intercept would change, and then it would become the final score, being the intercept or the constant. It would become the final score of a student with 0 attendance, and I think we actually see that here. Before I go ahead, so centering the score variable simply Huh? Sorry, and it simplifies our interpretation, just a typo, got caught up on. It simplifies our interpretation of the results, and it more precisely estimates the average treatment effect right after and right before the cutoff. So yes, so this one does. So instead of having a centered attendance value, we don't. And so this is where we get a little confusing here, and it's not super helpful. We do get the exact same treatment and attendance coefficients, but our constant became a negative 25, whereas when we centered it, it was 66.41. Once again, I'm going to get annoying here probably. This represents the average score we would expect with an attendance being 0 in the centered value 0, which would represent the median or that cutoff threshold we talked about. Okay, so we get an average score with a median at the median. Now, if we were to keep attendance as is, this literally represents what the expected score would be if a student had 0 attendance. That's not very helpful because a negative 25 isn't actually possible, but that's mathematically what it represents. So that's just a comparison there. Okay, moving on. Okay, so now we are going to look at a visualization. One thing I wanted to point out, it's not related to this lab directly, but when I read through this the first time, I got really confused on this part when I was in this class. So it kind of says it nonchalantly, but in order to assign a color palette, it says we need to modify our dummy variable to represent 2 and 1 rather than 0 and 1. And I got so caught up on why this was necessary. And it finally dawned on me, or I finally realized that in order to assign a color palette, so for the function here for color, it doesn't work with a zero. So if you use a zero value, so if you assign the, if it was color equals data treatment, just treatment, which is a 0, 1 value, that zero, R is not necessarily great at calling on a zero. It's not representative of a color palette. So all that to say, this is not super important, but if you read through this and you get caught up on it, the reason they do that is just simply for the color function here and the color, or pardon me, the argument, the color argument. So, anyways, not important, but don't get caught up on that. So, if we were to look at that visually, again, we're working with the centered. So that's why we have the negative values on the bottom. So this is the attendance value centered, where we subtracted the score itself from the cutoff, which was the median. So here's going to be our average. We have our treatment group, those with lower attendance that are put in the mandatory attendance policy group, and then the control group, those who were above the median attendance and they were not in the group. So we would have once again our constant representing this average right here, right at the cutoff. What would our value be, which was the 66? We have the jump represented by our treatment, beta 1. And then we have the slope itself representing as you'll notice they have the same slope. That's representing as attendance increases by 1 unit, the score goes up 1.16 points, I believe it was. So visually, you can see what this would look like here. Now, like we reviewed earlier, the counterfactual is pretty straightforward. We just set the treatment to 0. So what would the final grades been had the treatment not occurred? So if we were to plot that out here, we can see the counterfactual values, the treatment values. Interestingly, they don't include any lines here, but you can see that there is a jump between the counterfactual, what otherwise would have been without treatment, which, as we've already seen, it just stays on the same trend that would have otherwise been um, had the treatment not occurred. So the same intercept here. There's no jump in the intercept, but we can see the counterfactual. All right, now we're going to move into the replication of a study section here. So we want to look at alcohol consumption on mortality rates. Now, RD actually is a kind of a natural option here because with young adults, it sort of naturally selects into groups. So we have the cutoff being 21. So young adults who are below the age of 21, not legally allowed to drink. Young adults above the age of 21 are. So we have a otherwise known as a sharp regression discontinuity. As I mentioned earlier, I think I called it just your traditional one, where you have a sharp cutoff and then you have the fuzzy cutoff. So this is an example of a sharp cutoff as well, the age of 21. So we want to compare the mortality rate between these two groups. So hypothesis, young adults who consume alcohol have higher mortality rate. You can get the data, run through this yourself if you wish to. We have all of our data listed here, variables. So we have the age of the individual. Study focuses on adults between 19 to 22. So again, just below and then just above that cutoff there. So we have 2 years of data before, 2 years of data after. So 19 and 20, then 21 and 22. Mortality rate for alcohol related causes, mortality rate for homicides, mortality rate for suicides, mortality rate for car accidents, drugs, mortality rate for drug related causes, not counting alcohol. And then we have mortality from other external causes. Get some statistics here. So now before we run this, we want to create two variables. One's going to indicate young adults over than 21 and younger than 21, so treatment. We need to determine our treatment, excuse me, or create the treatment variable. And then the second is going to be the centered rating score, which is going to be age in our instance. So very simple with an if else function. If the age is over 21, we get 1 for our treatment. Sorry, I should cover that up there. We get 1 for our treatment. If below 21, it's 0, thereby being our control. And here we do the centering. So we take the age and we subtract it from our cutoff, which is 21, because once again, 21 is the age to drink, legally, should say. And here we go. We got some more of our data here, jumping into the analysis. Okay, so now we've got four models, all of which are using our scented variable. We have treatment. You'll notice our outcome we're looking at is all different. And we'll see that right below here. So now interpreting these coefficients. So we have 3 statistically significant and positive coefficients for treatment. One relating to all cause, car accidents, and alcohol, where drugs is not statistically significant. So we observe a significant and positive difference between the control and the treatment groups. So young adults who consume alcohol have higher mortality rate compared to young adults who below the drinking age. Pardon me. Class, I apologize. My baby was crying, so I had to step away for a minute. I am now back. Uh, as the usual, I forgot where I left off. So let's just go through it again. So we ran the 4 models, one looking at all causes, one with car accidents, and one with alcohol, and then another with drugs. And we can see that there are 3 statistically significant ones, with one that is not statistically significant, excuse me. So there is a goodness gracious, there is a statistically significant effect of all-cause mortality on the treatment group. Treatment group again being those who are over 21, above drinking age, in the 3 categories of all causes, car accidents, and alcohol. Once again, our mean centered, or excuse me, our scoring variable was centered. And so we have our constant here representing the average of the control group at the point of the threshold. So we have our average scores here at the point of the threshold. So once again, at the age cutoff, we have our slopes representing for each additional year of, uh, additional year in age, we would expect to see this slope. So interestingly, we can see that there is a negative. So at the age of 21, which is our cutoff, we would expect for every additional year, there would be a decrease in, I forget how they reference it. I assume this is the data, excuse me, I assume the data is based on some kind of per capita, but I'm not totally sure and I don't think it actually describes it. So let's just go with the assumption that it's per capita. So per capita, we'll see a decrease in all-cause mortality for every additional year after 21 of about negative 0.975. Now, car accidents, we see the same thing. And this kind of, sorry, this isn't statistically significant for the all cause, but it is for car accidents. And interestingly, you might not expect it, you might expect it, but for car insurance, we all know that younger people tend to have higher insurance rates. So it would kind of make sense that as time goes on, insurance rates go down because there's less car accidents if you're a little older. That's completely outside opinion, but interesting finding. And then we have a non significant but positive effect on alcohol. Now, interestingly, we do see a statistically significant um, positive slope for drugs. So for every additional year, after the age of 21, we see a positive slope of 0.378. So for every additional year, the mortality rate for drugs goes up. Okay, all right, now we're going to go on to looking at some of the results plotted. So we have here just looking at car accidents. Man, I cannot draw a straight line. Car accidents and the age once again centered. We have our treatment group, anything over 21, says 0 again because we centered that. And then control group prior to 21, so 19 and 20-year-olds. And then we have 21 and 22-year-olds. So we can see the same slope, negative. So there is a reduction over time in car accidents. However, right at the point of treatment, so at this transition period, there is a statistically significant increase. I believe it was statistically significant. Yes, increase. So at the age of 21, at the age of drinking age, we see, or at the age you are legally able to drink, we see a big increase in uh, fatal car accidents or mortality rates with car accidents. Yeah, sorry, mortality rate for car accidents. Okay, so that should be pretty straightforward. Now we're going to cover some of the primary threats to validity, of which there's two. So first, we are assuming that the relationship between the rating variable and the outcome variable is linear. So we're assuming that it's going to be on the same line here. So when it's nonlinear, you would need to include a quadratic term or complex polymers if the relationship is curvilinear. So it might not be linear. So we got to check our data prior to, pardon me, prior to going forward with with an RD. So check your data first. Assuming it's linear, we can move forward with how we've already gone through this. Now, another possibility is that once a non-linear, excuse me, a non-linear relationship is modeled correctly, the discontinuity disappears as it was caused by perhaps a misspecification in the model. So we can see that here in 4.3. So the bottom line is the correct relationship. It's in the curved line. However, if we modeled it as a linear relationship, we would actually be misinterpreting this as a treatment effect. So you just want to be sure to check your data to make sure that you're doing it correct, or pardon me, moving forward with the correct model. And to be more specific, when I say check the data, it goes back to what we covered at the very beginning of the lecture, where we need to test the relationship between our rating variable and the outcome variable right around the cutoff. So that would just be a first step, is making sure that once again, the relationship between the rating variable and the outcome variable related, just scaled or came back to the very beginning of our lecture. So once again, the criteria for the qualification or the scoring variable, the unit or measurement that we're using to determine the program criteria, whether you're in or out, it has to be highly correlated with performance itself. So once again, doing well on a standardized test and college GPA, let's see, the scholarship for college students with low income, we know that the income is highly correlated with college enrollment. Okay, so that's what we mean by that. You got to check your data. And now for that second threat to validity is diffusion of the treatment. So when we're doing the regression discontinuity, we're assuming that all individuals below or above, depending on what our cutoff is, what the treatment is, received the treatment. So we're assuming that everybody on one side of the cutoff, we'll just call it treatment over here, control over here, we're assuming that everybody in the treatment side received the treatment and everybody in the control side received the treatment. Now this may occur, so it lists in a situation where perhaps the rating variable, it deterministically defines who receives the treatment and who does not. So a program based on income, like rent subsidies, but that may not always be the case, or the control group or the treatment group may become contaminated. So for some examples, even though there may be a mandatory attendance policy, like in one of the earlier examples, some students may just completely disregard that. Or if you look at enforcing law on the international level, some countries might not implement it right away, despite being eligible. In other cases, let's see, what do we got? Individuals below or above the cutoff might be allowed to attend special classes or programs. Now, these crossovers or the contamination, crossovers and contamination are the words to keep in mind there. They might affect the estimation of the main effect. So this is where we get into the fuzzy regression discontinuity. And once again, this is where that cutoff, it's not deterministic, but probabilistic. So we're assuming that individuals should receive the treatment, who should receive the treatment, excuse me, are actually receiving it and vice versa. So among the ways to solve the problems, you can simply acknowledge it and then continue forward with your regression, comparing the eligible and ineligible individuals. And you can also use eligibility as an instrumental variable as a callback to last week's module, where first you can estimate sorry, this pardon me, this is worded funny. So the first step here would be predicting who actually receives the treatment. So first you estimate you receive the treatment. So sorry, that's a confusing mistype there. So once again, the first step is predicting who actually receives the treatment based on their eligibility. And then the second step is using that predicted treatment to estimate the effect on the outcome. So just like we did in the instrumental variable module last week, same two-step method. Ultimately, this aims, pardon me, to estimate what's called the treatment on the treated (TOT). I think everybody should be familiar with that from program evaluation, or maybe that was research design. It was either PAF 511 or PAF 541. I forget the order in which you're taking these. So either way, that's TOT, or treatment on the treated. That's ultimately that means oh sorry, it's the effect of actually receiving the treatment uh, for those who were supposed to receive it. So it's a way to try and determine what the treatment would have been if all those who received the treatment would have received it. Okay. And that's when we had talked about again. So fuzzy is when we have some fuzziness in there and it's not as clear. And sharp, like we talked about at the very beginning, or as I think I referred to it initially, traditional regression discontinuity. That's when we just have a very clear cutoff, and we make that assumption that everybody on the respected side actually did receive the. And here's some additional resources if you'd like to go through it. But for our lecture this week, everybody, that is it. Reach out if you have any questions. Again, go through this on your own, recap anything that didn't make sense. The lab is once again straightforward. I won't go through the whole thing with you, but you have 4 questions, 100 points plus some bonus points. So make sure you're getting ahead of this and not procrastinating to the last minute. All right, everybody, thank you for your time. We'll talk to you next week.